Quantum, I'm right here.
Chat rooms. So.
Yeah, I got the chat room right here.
Got the chat room right here.
Yeah. I figured I'd move forward so they can hear me. Yeah.
Delay for a couple seconds. You can usually.
Yeah, right.
This is a space test. Yeah. This has been Carrie's somewhere.
She's upstairs.
Upstairs, probably talking about dirty effing hippies in space.
She's actually not feeling well right now, so she's just sitting down. I told her to come back and take care of her. Instead, I decided to talk about SeaDragons. And now that's recorded. So I'm in so much
You're
trouble.
in so much
Because
trouble.
I'm going to come up with some excuse, and then she's going to watch this archive and be like, I knew it. I knew it.
This here 2 hours ago.
All right, so they want you to start already.
Start already. All right.
Fine, QG.
All right, Quantum. So I wanted to have a discussion about ultra heavy lift vehicles and the paradigm shift that it can cause in how we design and build the things that we fly. We got to have a little bit of a discussion about the really big stuff like SeaDragon that were proposed to be built in order to try and build really heavy lift vehicles just as cheap as it can possibly be done. Bob Truax did this design for Aerojet in 1962. And I don't know how well this translates, the view up here, but you have up on the screen, can we see the screen from the chat room?
Let me find out. I'll make things happen.
All right. Go to the Wikipedia page and look for SeaDragon rocket. Okay? So you'll find it up there regardless. But if we can get, Ben's going to tweak the camera for us here so we can see this up on the screen. So this picture is in the yellow section. Rocket goes from about here to here. All right? By comparison, Saturn V is about that big. Saturn V is also, here's the width of the nozzle on the first stage. The entire Saturn V is that wide. Okay? The entire second stage of the Saturn V will fit inside the nozzle. So you're talking about a freaking huge rocket. You're talking about a rocket that's 500 feet tall and has a nozzle 75 feet across. Okay? You're talking about a mind-bogglingly huge rocket. But Bob Truax's point of the engineering that he was trying to figure out is, what's the cheapest way to build a really heavy lift rocket? And the reverse of that is, what is the most expensive part of doing the rocket engineering? All right? And as it turns out, the most expensive part of the rocket engineering is the complication of the rocket. How complicated is it? Is linear with cost. So he said, let's make it as simple as we can make it, and make it as big as we can build it, because size, as it turns out, doesn't actually matter in terms of cost. The bigger you make it, it doesn't make any difference to the cost. It's not linear. It's less than linear. What ramps the cost up is the complexity of the rocket design. All right? So the space shuttle is very expensive because it's very, very complicated. All right? Not because it's big, because it's complex. So he said, let's make it as simple as possible. The simplest engine that we know how to make that has any kind of decent specific impulse is a kerosene oxygen blowdown engine. All right? Guess what? Armadillo Aerospace and Maston Systems use liquid propellant, liquid oxygen blowdown engines. Why? Because they don't require any pumps. You open the valves and light it, it goes. You know, you can control the valves. Valves are an issue. You've got big valves. On this thing, you have, you know,
Big valves.
Big valves. But the specific impulse of this engine is in the 280 range. Okay? Which for a blowdown engine is really good, because as it turns out, the chamber pressure has less effect on specific impulse when you get to these really big kinds of things. So you can make it, it doesn't have to be super high pressure. The propellant and oxidizer pressure doesn't have to be super high. So the simplicity of this thing is, it's got 3 tanks in it. It's got RP1, which is basically highly refined kerosene, rocket propellant 1. It's got liquid oxygen, and it's got a nitrogen pressure tank. And they just open the valves, and the high pressure nitrogen forces all the stuff down into the thing, and you ignite it, and it goes. All right? So it's really simple. But this thing would be able to put 1.2 million pounds to LEO. And it's got a fairing diameter of 75 feet. 75 feet. The biggest thing I think we can launch right now is about 15 meters. I think it's about the big. How big is the shuttle payload bay?
That's not the biggest thing you can launch, is it?
It's about the biggest diameter. I mean, that'll launch a section of the space station.
Help us out.
Somebody out there know what the largest diameter. It's in the. I think it's in about the 30 to 40 foot diameter range. That's probably the really big fairing you can put on a Delta IV Heavy. You might actually be able to put a slightly bigger fairing on an Atlas V, but it doesn't have the loft of a D4 Heavy. Actually, the Proton may have a bigger envelope, but it's still not 75 feet. So you talk about these really huge things and be able to put this giant. I mean. 75-foot diameter satellite that weighs 1.2 million pounds.
How wide do you think this room is?
I don't know.
Anyone rough guesses?
No.
I mean, we're talking
It's probably
about
it's probably in the 40-foot range.
We're talking about something that's
maybe
like as large as this room or larger, right?
You're talking about something that's twice as big as this room. Almost. I think this room is about 40 feet across.
At this point, we can start measuring in football fields.
It's huge, yeah. I mean, it's 25 yards. Okay, it's 20. So it's 25 yards. So it's a quarter of the diameter of a football field. Right? And then we're going to launch this thing out of the water, which was really pretty cool. This actually has ballast tanks, and you probably changed the camera already.
You want me to go back?
No. Let's say the rocket's this tall. Well, at launch time, this much of the rocket's actually underwater. They actually float it out horizontally out to the launch area in the ocean. Then they change the ballast tanks, and they basically tip it up this way. They sink it down in the ocean. They put the payload on top. They change the ballast tanks and float it back up until it's just about 50-50, a little bit heavy so it stays vertical. And they launch it out of the water. So there's no launch pad, there's no tower, you've got to build some kind of a rig to go around it just to keep it out in the ocean. But actually then you float that away. So you can probably largely do this off of an oil drilling platform, which is basically a big ship. Those things actually float in the ocean. So it's basically you could buy a drilling platform and float out there. Now, the aerospace companies at the time said, there's no way you can build this in any kind of cost-effective manner, right? And Bob Truax didn't believe him. So he got NASA to, he bypassed NASA at that point and the aerospace companies in 1962, and he went to the shipbuilding companies. And he went, I want to build something that's 75 feet in diameter, and it's built out of steel. And it doesn't have to be aluminum. I want it as cheap as possible. And the shipbuilding companies went, oh yeah, that's basically a submarine hull. No problem. When do you want to start? So, I mean, that was his basic thing. You take an existing submarine hull design, you put a rocket motor on the back end, you put propellant tanks in it, turn it up, and you fly it.
To answer your question, 4.6 meters by 18 meters is the shuttle cargo bay.
4.6 meters, right? So that's only about 15 feet in diameter.
15 feet by 60.
15 by 60. So, yeah, this is 5 times that diameter. 5 times the diameter of shuttle bay. Think about how big that thing is. Well, here's the thing I just wanted to try, and it occurred to me the other day. If you could take a really big thing that we're currently building, let's say James Webb Space Telescope. James Webb has to be launched in this folded up configuration. I don't even know what launch vehicle they're using. Probably a Delta IV, might even be a D4 Heavy.
At this point, I think they're going to just build their own launch vehicle.
They might. For all the money that they've spent and all the time that they've spent, they could have built a launch vehicle. But that's exactly the point. If James Webb could weigh up to 1 million pounds, and it could be 75 feet in diameter, you could launch the thing fully deployed and build it out of welded steel. You don't have any deployment mechanisms. You don't have all these billet aluminum. You don't have all these machining costs. You just you just build it out of, and yeah, it's got to survive launch. But if you could build it out of welded steel and it could weigh 1 million pounds, who cares? You can make it as heavy as you want. You can build it out of anything, And the reason that we don't build things out of steel is, number one, it's really heavy. So we build things out of aluminum. The problem with aluminum is that you can't braze it in such a way that you guarantee that it's going to survive, because the brazing isn't as strong as welding is for steel, right? And so you build things out of basically what's called billet aluminum. You take
visual examples.
Show and tell. This is part of the chassis from the LRO's Propulsion and Deployment Electronics box. And I guess you can kind of see, you're going to zoom in here? Yeah. Nice having a cameraman. Thank you very much. This is machined, this box is machined from a single block of aluminum. There is no brazing, there is no welding, there are no mechanical points of all there's studs that are standing up inside of here. They're all machined. This was one big block of aluminum when it was made. And the reason is because we know structurally that this is going to stand up to the vibration environment of launch, and it's not going to change with kind of temperatures and things like that. So this is generally how we make these kinds of things today. If I didn't care whether or not this weighed 50 pounds, I would just weld it together out of steel. It'd be way cheaper. It just wouldn't matter, So those kinds of considerations are the paradigm change that I wanted to talk about. And like I said, it had just occurred to me, if you could build James Webb, and it could be, as big as you wanted and weigh as much as you wanted, you could probably have saved, I don't know, probably $1 billion off the cost of the satellite. Well, guess what the rocket would cost to fly? About $1 billion. All right? You say, well, $1 billion is a lot of money for a launch vehicle. Yeah, but it's 1.2 million pounds. It's only $800 a pound. $800 a pound? The current launch costs are $10,000 a pound. I'm ballparking that number at $1 billion a pound.
Estimated launch cost $1 billion per launch.
In 1962 dollars, they were talking about $600 a pound. Now I don't know. There's a website that'll tell you that, and I just haven't taken the time to look it up. But let's say it's 5 times that cost now. Let's say it's $3,000 a pound. It's still a third of the cost. Now the rocket would cost $3 billion to launch. But how much money could you save off of how many satellites could you launch off of that? Right now you're basically restricted to the largest fairing that you can put it in, which is on the order of the space shuttle size, which is about 15 feet in diameter, and you're constrained to the largest launch vehicle in the U.S. inventory, at least, is a Delta IV Heavy, which is 50,000 pounds to LEO, all right, or 25 tons, right? This vehicle's 550 tons. NASA's talking about designing and building a heavy lift vehicle. It's in the Senate's version of the 2011 budget. It's 125 tons to LEO. This is 4 times the capacity, and it was designed 50 years ago. Why aren't we flying this?
I have a question. I'm old enough to remember the next successor to the Saturn V was supposed to be the Nova rocket.
Right.
I would think those two would have been come up with or designed basically at the same time. Why did the Nova rocket get the attention and not this one?
I don't know. I really don't know.
Because this is the first I've heard of this. I remember hearing about the Nova. I'm 12 years old.
I think I first read about this in Dennis Wingo's book Moonrush, and I went, "How big was that?" And I went and started looking at it, and in fact, can you zoom out and show the screen again? This very grainy black and white picture is from the PDF files from the Aerojet General Corporation, NASA, and as evaluated by TRW Aerospace, which is now the Northrop Grumman Aerospace Systems sector. So the group that did the evaluation still exists. Aerojet still exists, right? The shipbuilding organizations still exist. There's not any reason that this actually couldn't be done. And we know how to do it way better than they knew how to do it 50 years ago. You know, I mean, if you could get this to $1 billion a launch, then you're talking about $800 a pound of LEO, and you're talking about £1 million.
Yeah, but QT brings up a good point, which is the NASA guys would be saying, what's the need for all that lift?
What's the need for all that lift?
And then on the flip side of that, you know, when you look at it from, you know, I look at it from IT, I give my engineers, my software guys more available storage, more available I/O, what way that's lift. They just use it needlessly.
They just use it all up.
Because now they can.
Because they can. They can, yeah. The software will expand and fill all available capacity in both, computation and size. But the point is, if you could take something like James Webb Space Telescope, which I think at this point is about $4 billion, and you could make it as heavy as you want and as big as you want, and how much could you reduce the cost? I think that you could probably reduce the cost $1 billion. Because the complexity, again, the complexity is linear with cost. So the complexity goes way, way down if you don't have any deployment mechanisms. You launch the thing basically intact and fly it.
There's actually a question.
Question?
Apparently gasified oxygen and hydrogen due to pressurization put
Gasified hydrogen and oxygen due to pressurization.
Put a dent into the SeaDragon first and second stage in their mass estimates. Any comments on that?
Nope.
Okay.
Sorry. But these PDF files are referenced in the Wikipedia page. You can go and you download them. I did that just the other day and started reading through them. And a lot of that's all addressed. There's technical hurdles that have to be overcome. They did do some launches to validate the launch concept of launching these things out of the water. Pretty big things for sounding rocket size. I mean, they weren't getting up even to a Delta II kind of size, but they were pretty good size, and basically everybody enthusiastically endorsed how easy it was to launch them out of the water, right? Because you don't have to worry about all the land-based infrastructure in order to do that.
That sounds weird, but what's the environmental impact of having that much pressure down?
You're gonna create essentially a sonic environment inside the water. I mean, the environmentalists and the whale huggers will probably go berserk because you're freaking the whales out around the world when you do it. You probably deafen the whales or something. I don't know.
But I mean, what kind of impacts are we looking at? Is there going to be an unforeseen consequence? Obviously, it's unforeseen.
An unforeseen consequence is a little hard to figure out at that time.
But it's hard to foresee what may happen. But
it's called an unknown in the satellite world.
Well, I also think if you're using that much steel, a lot of that is going to make it through reentry.
Well, the whole idea is that the whole first stage would be reusable, because I think the first stage was 6 centimeters thick steel. I mean, it's basically a submarine hull. And so they were going to slow it down with drag chutes, but then it was only going to go first a couple of minutes. The first stage would burn out in just a couple of minutes. And so it would only be like 20 by 30 miles down range. And 20 miles up, 30 miles down range, and you pull it back in with a drogue chute and just let it splash down in the ocean, but almost at speed. I mean, you would just it would be like a controlled fly on the drogue chutes, and then you would just slam this thing into the ocean because it's made of steel that thick, and it's going to be fine. It's not like you have this, thin aluminum shell or anything. It's like, whoosh.
Well, what if we modernize it? What if we used a next-gen metal or even aluminum or something like that?
Zellanium,
To try to take its weight down instead of...
Oh yeah, if you could validate that you could build something like zellanium. You guys heard of this? This is a new metal that came out just actually the first of 2010. That's carbon nanotube and aluminum composite, essentially. That's as strong as steel but weighs as much as aluminum. Essentially, it's a carbonized aluminum like steel is carbonized iron. It's the same kind of thing, but somebody figured out how to do it, and I think it's being put out by Bayer, B-A-Y-E-R, the same people that actually make the aspirin. They're a large consortium, and they licensed this stuff from this guy in Germany. They're already making parts for bicycles, really high-end bicycles, but it's as strong as steel but weighs the same as aluminum. So yeah, if you could validate something like selenium, and that doesn't even have to be evaluated from a flying in space point of view. We don't even need to know how that's going to react in a vacuum environment, because it's not going to go that high. It's going to go to 20 miles. You know, so yeah, if you could do that, then you could cut tonnage out of that and actually get even better performance. You know, so I was just wanted to kind of initiate a conversation and get people to think about, if I could make this, how cheaply could I make the satellite, and how could I make it work with this kind of a technology? I mean, remember this 2001 Space Odyssey? The big ring-shaped space station that rotated and generated gravity? Why haven't we built one of those? Because it costs too much. Why? Because we got to loft all this material up. My back-of-the-envelope calculations show that you could actually fly that in 3 launches with this. So you could fly that for $3 billion. I mean, that's a big space station, But it's just a whole mind change. It's a game changer, just to be able to do this. And one of the things about the way that NASA currently works is everything's a mission. You've got to have, and that's one of the things that NASA and the chief technologist and the Obama administration are working against right now, is saying, look, what we want to do is we want to develop technology. It's almost if you build it, they will come, right? If you build a capability that doesn't exist today, somebody's going to figure out how to use it. They're going to figure out a mission to fly on this. If you had this, they'd figure out a mission to fly 1 million pounds of LEO. Why they would want to do that? I mean, the entire constellation infrastructure, in order to put a base on the moon, 1 launch. 1 launch. So it's just a game-changing technology. No, it's not bombing. It's going there. So I want to go to the moon. The moon inspires people. You talk about, you sit down and you talk with a group of kindergarten kids, and you say, you could be the next astronaut to land on the moon, and their eyes get big. I go out and talk to educational groups sometimes, and I was talking to a group of three classrooms of 6-year-olds. 65 kindergartners sitting on a rug. That's talking about space. It sounds like either a recipe for disaster, or just pure awesome. Well, these kids were awesome. And you talk about space, and I can demonstrate simple things of orbits and things like that. If you want to inspire kids, you talk about, here's the moon. They can walk outside at night and see it and go, I could go there. I could go there. I mean, it's not like Mercury or Mars or those things are so far away. They're a dot in the sky. The moon's like, so you really inspire people. And I think that's one of the reasons why I was a fan of the whole constellation program, is because it was going to put us back on the moon, and it's not a been there, done that kind of thing. The inspiration that you give your students is probably worth the cost of admission, and you get a moon base for free.
How can you get a SeaDragon or an ultra-heavy lift vehicle be a SeaDragon or something else in your production somewhat? What's holding us back? I
mean, I'd love to see, Aerojet and Northrop Grumman have actually, and you could pull in somebody who's an expert in, blowdown engines, like, Armadillo or Maston Aerospace. I know Dave Maston's not a big fan of heavy lift, and I agree with him in some ways. But there's enough knowledge now that you could actually put this together as a commercial venture. I mean, it sounds like a crazy thing, but you say, hey, look, NASA, I can launch 1.2 million pounds to LEO, and I'll do it for $2,000 a pound. It's 1/5 of your current launch cost if you promise to buy 5 of these vehicles. All right? Over time, that's $10 billion. That's a lot of money. That's half of NASA's current budget. Right? Per year, right? It's $2 billion per launch. All right? But the cost of developing the heavy lift vehicle and building the prototypes and everything else is about the same. And then a commercial entity would own the launch capability. And NASA would be on a pay-as-you-go commercial launch capability. And if the costs pan out the way that they look like they would, then the commercial company would have reduced the cost of LEO by a factor of 5 and would be making a 100% profit per launch. Right? They'd be making $1 billion a launch, and NASA would be saving, I don't know what the number is, huge. They'd be saving a lot of money on the launch costs. Just think about it. You could launch, the EOS satellites, Ara, Terra, and Aqua, those 3 satellites, and 5 more the same size could all be launched on one launch.
There's one downside to launching all of that on one vehicle.
You lose it, you're done.
You lose it, you're done. Think
Yeah.
of how much money and time is invested into all these programs.
Yeah.
You know, and think of how much math can be thrown on that thing. You're going to optimize every ounce on that rocket as you always do.
But the point is you wouldn't have to.
You probably still would, though.
You probably still would try and optimize the total mass just because engineers are engineers. But perfection is the enemy of good enough. And if you could build this out of welded steel and fly it, good enough. We're done. And that would be a paradigm change in and of itself, you know, to have a launch vehicle that's good enough rather than perfect. You know, or, you know, so if you're not pushing the envelope to the nth degree of the engineering, you know, getting to the 80th percentile of capacity is easy. Getting to the 98th percentile of capacity, that's hard. And that was one of Bob Truax's key things when he designed this, is trying to figure out, you know, what's the cheapest way we can build something, and it turns out size, in terms of cost, didn't really matter. So, any other comments or questions? Any other thoughts? You know, I'm not a, contrary to Ben, I'm not actually a rocket scientist. I'm a software engineer. I'm not even a hardware guy. I'm just a space enthusiast and you know, software engineer. So I just learn about this stuff because I love it.
I remember hearing the name Bob Truax growing up. I forgot who he is. Do you have any background?
He was. That's a great Wikipedia search because he was a real maverick and a brilliant guy. He rubbed a lot of people the wrong way, I think, but his designs were freaking brilliant.
Did he ever get involved in the cars at Bonneville?
I have no idea. Bonneville cars? Yeah, I have no idea. He might have.
Where I heard
He might have. You know, he got involved in a lot of stuff. He wanted to put. I don't remember who told me this story. Might have been Porkchop. Told me the story that Bob actually had a design that he wanted to put a man on the moon as a private enterprise, and he contacted Evel Knievel, who turned him down. I think it was Porkchop that told me that story. That would have been the ultimate stunt.
Get him back.
Yeah, I don't know, but
Maybe
I
that's
mean,
why he turned it down.
that's pretty funny. Wow, it looks like lunch arrived already. Cool. Or either that or it's Thick Geek. I can't read the boxes. A whole bunch of people just came in with big boxes.
So there are no current plans for heavy lift rockets?
The current plan for a heavy lift rocket is in the Senate version of the NASA appropriation bill for 2011. And I think that the story is that NASA has basically already said, we already know what the design is going to be. We're ready to go build it. And so Senate said, don't go wait until 2015, start building it now. Take the design that you already have, which is basically the Ares 5 inline rocket, and go build that. It'll use space shuttle. I think the design is not the side-by-side. I think it's the inline rocket, what they're talking about. In fact, there was a great article at SpaceRef. I don't remember the author's name. This last week, talking about the Senate appropriation bill and this very specific language that the senators use in order to drive a very particular design in NASA. And the question was, should the Senate be designing rockets? And my answer was, frack, no. The Senate needs to say, we want a heavy lift vehicle. We want to be able to do these kinds of things. You go figure out what the best way to do it is, as opposed to referencing the experts in Utah, which, you know, they want to build solid rocket motors because that's what the experts in Utah build. Well,
More cash for them, right?
more cash for them. And oh, guess what? You know, the senator from Utah is the one who said that and put the language in the bill. I have a problem with that. I don't have too much of a problem with the design, because basically what they're talking about doing is taking a space shuttle tank, space shuttle solids, putting the space shuttle main engines on the bottom rather than piping all the fuel out through the into the shuttle and then through the engines. They're just going to basically run the tankage straight down and put the engines on the bottom and then put a whole second stage on top. So they're talking about 125 pounds to LEO, 125 tons to LEO. It's like it's like an N price rocket. 125 pounds to LEO. It's about 125 tons to LEO. This would be 550 tons to LEO. You can see how big this thing is if you look in the PDF file, and actually on the Wikipedia page too. There's a picture of this thing floating next to an aircraft carrier. It's half as long as the aircraft carrier, so it's pretty ginormous. I think there's some other pictures in here. A lot of text. This is an old scanned, document from the 1960s. Can we go to the cutaway on this, Ben?
Which is my command. Yes.
Okay. This is the first stage from here to there. This is the second stage. The second stage was hydrogen oxygen. So the second stage, this is the nozzle for the second stage, and the tankage runs up here. So the first stage is a small portion of the rocket, and this would actually be built to be reusable. The nozzle from here to here on this picture, this much of the nozzle, the entire Saturn V second stage can fit inside that nozzle. So it's a really big thing. It would be amazing to see it launch. I can't imagine how much sound it produces.
The Pacific Islands got to be wary when that thing takes off.
I don't know. I mean, it would be 200. I mean, think about this. It would be 200 feet down in the water, almost 300 feet down in the water, the bottom of the nozzle.
Huh? It could cause a landslide.
Sonic waves, possibly.
It's going to cause a
You could do something like that depending on how.
Yeah,
it is.
I mean, there's certainly.
That's the question. Too.
That's a big That's a big thing. I don't know how loud it would be. It'd be frightening. Food is ready. So we are done here. Any further questions? I had two NutriBars and some coffee here for breakfast, so I'm ready for potbelly sandwiches. Any other questions from the chat room?
How wide or long is the SeaDragon?
75 feet wide and 500 feet tall.
Does that answer your question, QG?
He's a big rocket man. QG ought to know that off the top of his head.
They said thanks.
All right.
There you go. They said have good luck.
Lunch. The rocket. And the reverse of that is, what is the most expensive part of doing the rocket engineering? All right? And as it turns out, the most expensive part of the rocket engineering is the complication of the rocket. How complicated is it? Is linear with cost. So he said, let's make it as simple as we can make it, and make it as big as we can build it, because size, as it turns out, doesn't actually matter in terms of cost. The bigger you make it, it doesn't make any difference to the cost. It's not linear. It's less than linear. What ramps the cost up is the complexity of the rocket design. All right? So the space shuttle is very expensive because it's very, very complicated. All right? Not because it's big, because it's complex. So he said, let's make it as simple as possible. The simplest engine that we know how to make that has any kind of decent specific impulse is...
I'm going to come up with some excuse, and then she's going to watch this archive and be like, I knew it! I knew it!
It's here 2 hours ago.
All right, so they want you to start already.
Start already. All right.
Fine, QG.
All right, Quantum. So I wanted to have a discussion about ultra-heavy lift vehicles and the paradigm shift that it can cause in how we design and build the things that we fly. we got to have a little bit of a discussion about the really big stuff like SeaDragon that were proposed to be built in order to try and build really heavy lift vehicles just as cheap as it can possibly be done. Bob Truax did this design for Aerojet in 1962. And I don't know how well this translates, the view up here, but you have up on the screen, can we see the screen from the chat room?
Let me find out. I'll make things happen.
All right. Go to the Wikipedia page and look for SeaDragon rocket. Okay? So you'll find it up there regardless. But if we can get, Ben's going to tweak the camera for us here so we can see this up on the screen. So this picture is in the yellow section. Rocket goes from about here to here. All right? By comparison, Saturn V is about that big. Saturn V is also, here's the width of the nozzle on the first stage. The entire Saturn V is that wide. Okay? The entire second stage of the Saturn V will fit inside the nozzle. So you're talking about a freaking huge rocket. You're talking about a rocket that's 500 feet tall and has a nozzle 75 feet across. Okay? So you're talking about a mind-bogglingly huge rocket. But Bob Truax's point of the engineering that he was trying to figure out is, what's the cheapest way to build a really heavy lift? Right, you're going to read
Well, I'm right here.
chat rooms. So.
Yeah, I got the chat room right here.
Got the chat room right here.
Yeah. I figured I'd move forward so they can
It's
hear
a
me
slight
out.
delay for a couple seconds. You can usually.
Yeah, right.
This is basically this is Ben carrying somewhere.
She's upstairs.
Upstairs, probably talking about dirty effing hippies in space.
She's actually not feeling well right now, so she's just sitting down. I told her
good.
I'd come back and take care of her. Instead, I decided to talk about SeaDragons. And now that's recorded, so I'm in so much trouble.
A kerosene oxygen blowdown engine. All right? Guess what? Armadillo Aerospace and Maston Systems use liquid propellant, liquid oxygen blowdown engines. Why? Because they don't require any pumps. You open the valves and light it, it goes. You know, you can control the valves. Valves are an issue. You've got big valves. On this thing, you have, you know,
Big valves.
big valves. But the specific impulse of this engine is in the 280 range. Okay? Which for a blowdown engine is really good. Because as it turns out, the chamber pressure has less effect on specific impulse when you get to these really big kinds of things. So you can make it, it doesn't have to be super high pressure. The propellant and oxidizer pressure doesn't have to be super high. So the simplicity of this thing is, it's got 3